This is an example of how to use the free body diagram method to analyze a compliant mechanism. And so we want to consider a compliant 4-bar mechanism. And so we're going to have ground, an input link, a coupler link, and then we're going to have a pin to a compliant output link. And so our compliant 4-bar mechanism will look something like that. And so we'll have ground, link 2, link 3, and link 4. And now when we go to our pseudo-rigid body model of that compliant mechanism, it will look like the rigid portion of the mechanism, rigid body portion of the mechanism doesn't change. And instead of this compliant link, we'll replace it with its pseudo-rigid body model, which will be a rigid link. And then we'll have a little bit of a longer section here that connects it to ground. And the compliance of that compliant section will be replaced by a torsional spring with some sort of stiffness K. And how we find that stiffness K is just comes from chapter 5. Okay, so really what we have when we look at this pseudo-rigid body model is just a 4-bar with a torsional spring on the joint between link 4 and ground. And so how we analyze that is we just do free body diagrams of links 2, 3, and 4. Now, in order for this thing to move, we need some sort of input, and so we're going to put an input moment on link 2. And depending on how big that input moment is, the bigger the input moment, the more deflection we'd expect out of that spring that's at that on link 4. All right, so we can do our free body diagram of link 2. And that's just going to look like we'll have the link. Where the pins attach to other things, we have to replace those with forces in the x and y direction. And so we'll have force 1, 2, x and force 1, 2, y on that lower pin, and on the upper pin we'll have force of link 3 on link 2 in the x direction, the force of link 3 on link 2 in the y direction. And of course we'll still have that input moment. Okay, and so that's going to be our free body diagram for link 2. And so once we have a free body diagram, we can just write our force equations and our moment equations. So we'll have the sum of forces in the x direction, and that is equal to F12x plus F32x, sorry. And if it's a statics problem, it's going to be equal to 0. If it's a dynamics problem, of course, we'll have mass times acceleration over there. Turns out dynamics problems get very complicated for compliant mechanisms, and so we won't actually do those. So the sum of the forces in the y is just going to be F12y plus F32y, and that's also equal to 0 in the static case. Sum of the moments, we have to determine where we're going to sum our moments about. And so if we have this point O2, or summing our moments about O2, what we're going to have, since force 1, 2y and force 1, 2x pass through that point O2, they won't show up in the moment equations because the moment arm is equal to 0 for both of those two forces. We'll have our input moment, and then we'll have the moment of this force 3, 2y about that. That's going to be a positive moment. It goes in the counterclockwise direction. And so we'll have F32y times R2, which R2 is just the length between those two pins, and then cosine theta 2, where theta 2 is the angle of that link, or the angle of the line between the two pins. Then we'll have the moment due to the F32x force, which will be in the negative direction because it'll be a clockwise moment, and that'll give us F32x times R2 sine theta 2, and that'll be equal to 0. Our free body diagram for link 3. Free body diagram of link 3 is going to look like, we'll just draw link 3. It's got 2 pins that we've disconnected from the rest of the system, and so we have to replace those with forces, and we'll have the force that link 2 puts on link 3 in the x direction, the force that link 2 puts on link 3 in the y direction. We'll have the force that link 4 puts on 3 in the x direction, and the force that link 4 puts on link 3 in the y direction. Okay, and so we'll have sum of the forces x is just F23x plus F43x equal to 0. Sum of the forces in the y direction is just equal to F23y plus F43y, and that's going to be equal to 0. We're going to sum our moments, do it about that point A. And so our sum of our moments is going to be, once again, we won't have any moment due to the forces that pass through A. We don't have any applied moments in this case, and so we just have the moment contributions due to force 4,3y and force 4,3x. And so they'll just look like F 4,3y times R3 cosine theta 3 minus F43x R3 sine theta 3. And that's going to be equal to 0. And then our last link we'll have a free body diagram of link 4, and what that's going to look like, we'll just have that, and we'll have the forces that act on the pins, which we'll have F 4, the force of 3 on 4 in the x direction, the force of 3 on 4 in the y direction, and we'll have the force of 1 on 4 in the x direction, the force of 1 on 4 in the y direction, and we'll also have the moment that acts on that pin, which we'll just call M4. Okay, and so this is the moment due to the torsional spring. All right, and so we'll have some of the forces in the x direction is just going to be F14x plus F34x equal to 0. Some of the forces in the y direction is going to be F14y plus F34y. It's going to be equal to 0. Some of the moments, call the point we sum our moments about 04. Then we'll just have M4 plus F34y times R4 cosine theta 4 minus F34x R4 sine theta 4. Okay, so we just have the force times the moment arm. And so this is just the cross product due to the forces. And so that's what you expect for moments. And all that's going to be equal to 0. All right, so that's just what the free body diagram equations look like for these for this problem. Now there's a few other notes that we would need to work on this and to find some relationships. The first one is M4. That's the moment due to a torsional spring, and so that's just going to be K, whatever the spring constant of that moment is, and we can get that from using the pseudo-rigid body model. But the moment due to that spring is just going to be whatever the current value of theta 4 is, which we'll just write as theta 4, minus the undeflected position of that so this theta 4 naught is the undeflected angle of theta 4 when that compliant link is not bent in any way. The other things that we'll have to have is there's some relationships between these forces. For example, F23x equals minus F32x, F23y equals minus F32y, and F43x equals minus F34x, and F43y equals minus F34y. All right, so those equations are enough for us to write. We've got a bunch of equations. We've got a total of let's see here, 13 equations, 14 if you include this one that we can write. And so putting those together, if we know the kinematics of our 4-bar, and we can do that just using the spreadsheet, a spreadsheet that we have, and I can post a version of this. And so we can do this in Excel and have it solve this 13 by 13 matrix equations for us. And so, but these are the equations we need using the Newtonian method. All right.